cardiac output monitoring. Okay, this lecture was taken long ago. So I am talking of 2009 or 10, maybe I would have taken this lecture. 2009 or 10. This is as old as that. Okay. In fact, maybe 2015 or something, not 9 or 10. Okay, it's taken in another hospital. Okay, and we need to have some baseline knowledge before when we talk about PiCCO. Okay, some baseline knowledge. So we did use a large amount of extravascular lung water index monitoring through transforming thermodilution using our Edwards Life Sciences device. Okay, now we are moving towards PiCCO. PiCCO is a little bit more expensive as compared to that with respect to consumables, but it probably gives us the same data. Okay, so let's first understand what is cardiac output monitoring all about. So we have to understand how, when, and why to monitor cardiac output. So in somewhere in 2011 there was this ASA conference, American Society of Anesthesiology conference. In that conference they met very good anesthetists because their ASA, their conference, and they were a big all qualified anesthetists who were there, not students anesthetists who were there. And what they found was they asked them which is the hemodynamic monitoring do you routinely use for management of high risk surgery patients. Anesthesia, so high risk surgery, which are you using? So it was surprising to know that invasive arterial pressure and CVP were the commonest things that they used. Commonest things, followed by non-invasive, and cardiac output monitoring came down there. Only 35, 34. I'm certain that this might be those patients who are liver transplant patients, most probably. Okay, so the use of cardiac output monitoring was extremely low. But what we are knowing now is that we are moving from extremely invasive modes. The Swan-Ganz catheter was an extremely invasive mode to a minimally invasive mode to almost a non-invasive mode. This is how we are moving in cardiac output monitoring. In for that matter, for everything that we do, we are moving from invasive to minimally invasive to non-invasive. So, non-invasive, which is going to be the future, which is probably going to be the future, is all of these: PROACT, LITCO, Rapid, recording analytical method. You know, all these things. T-line system, ESCO. Many of these are under. I'm telling you this lecture was 6-7 years ago, more than that. But still, many of them are still they're trying to find out whether this is working or not working. Of which the ECHO and the ASCOM are two things that are being used now regularly in Australia. Ultrasound guided cardiac output monitoring in ECHO, which is now being used regularly in Australia. I had used it for a while. It is a fantastic monitor, a probe that goes inside. We'll come to that. But what we now are still dealing with, are these methods. As of now, we are still dealing with the Swan-Ganz, the lithium dilution cardiac output monitoring, the pulsion cardiac output monitoring, flow track, the volume view. These are things we are dealing with, of which this is now not there anymore. Okay, so they can also be divided into two parts: the calibrated systems and the non-calibrated systems. Now, when you say calibrated systems, means I am doing some method and telling the monitor that this is the cardiac output, like zeroing. For example, an arterial line is 0, no? We tell the arterial line, okay, this is air and air is 0, so what you're seeing now is blood pressure. Isn't it? Similarly, there are monitors that need kind of a zeroing, also called as calibration. These are those ones. And that calibration can be done by either doing something called TPDT, which is transpulmonary thermodilution, or lithium can be used. And non-calibrated systems are these. They are not calibrated at all. Okay, so if I were to divide the whole thing, this graph is very important for you. If I were to divide the whole thing into various parts, you have cardiac output monitoring, which is divided into thermodilution, Doppler echo, clarity, and ultrasound guided cardiac output monitoring. This is one part of the story. Okay, pulse contour analysis that we talked about. Pulse contour analysis means it's looking at arterial line only. It is looking at arterial line only and giving you the cardiac output, right? Now this can be divided into two parts: non-invasive and invasive. This is what we used some time ago. Were you there when we put that small cuff on the? You were not there. So we had this system for a while, ClearSight. We had this system where we just put a small cuff, blood pressure like cuff on the finger, and that gave a waveform, and with that we got cardiac output. So I did that study, which didn't really work well. Okay, it didn't work well on our patients. So ClearSight, that was so ClearSight. We used that for a while. We used this. It was called volume clamp technique. That means ClearSight was you just put a small, this over here is uncalibrated system. You put the body surface area by looking at weight, height, and all these things, and you get a waveform, and the waveform will give you that, okay, this is the cardiac output. Non-invasively. But the invasive ones were divided into two parts. They are the calibrated and the uncalibrated. The uncalibrated is these ones, which is the preloaded data. For example, flow track. You understand the flow track? Have you seen the flow track? So the small thing in volume that we put, that small device that goes to the patient, that is the flow track. That small thing that we apply, that is called the flow track. So we've never used the flow track on its own. We've always calibrated the system. So if you put that device now also to the volume system, you will get a cardiac output. If I put just that system, I don't need to have the central line, and I just need the arterial line. I can attach the flow track there. The flow track will attach to your arterial line. Now it will look at a few parameters and give you cardiac output. Clear? So that is based on data that you have loaded. You have loaded certain parameters in that, and that's how it's giving you cardiac output. That's why it's called preloaded. You understand? Preloaded. Whereas the other system is calibrated. The system that we've been using, EV1000, and now what we're using PiCCO, is a calibrated system where we are telling the patient, telling the monitor, okay, this is the cardiac output. Now you accordingly adjust it based on your preloaded data. You understand? Huh? So there are certain methods, there are certain utilizations for all of these things. Let's go to what thermodilution is. That is the background of most of our calibrated systems, thermodilution. Okay. So 1870s, when he actually said, Adolf Fick, you know that in our ventilator we have Fick method, you've seen it? Next time you should see, Fick method is there on our ventilator. Our ventilator has got Fick method to find out cardiac output. You know this or no? So when you open our ventilator, you go to hemocalc. I've done it in the past. I've shown someone, I think I've shown Vaijanti and all. We have a machine in our ventilator on our GE, Cascade R860, where if you go to hemocalc, you add PaO2, you add CVP, you will get cardiac output. That's Fick's method. Okay, it's an indirect method to figure out cardiac output. So this Adolf Fick, who made that Fick's method, said it is astonishing that no one has arrived at the following obvious method by which the amount of blood ejected by the ventricle of the heart with each systole may be determined directly. This is what he said. So that comes with this Stewart-Hamilton equation. Later on, this Stewart-Hamilton equation came in, basically saying how much of blood is ejected out from the heart is basically your cardiac output. You can just find it out with that. Find out how much is ejected out. Okay, and so they come up with this particular formula in 1897 called as the Stewart-Hamilton equation. It's a very old equation. You understand? We'll come to that equation. We'll come to that. We'll understand what that is about. So this is what is this? What device is this look like? This is the heart. Understand? But what is inside?
Swan glands.
How do you know the Swan glands? So it's gone from the IVC. From the IVC, it's gone up from the right atrium, right ventricle into the pulmonary artery. I worked with this. I worked with this for 10 years maybe. Okay, where Swan glands was the sine qua non of everything, and still people still swear by it who use it. Okay, the Swan glands. Now this means with this we were actually figuring out something called as intermittent. Understand these words very clearly. Intermittent bolus pulmonary artery thermodilution cardiac output monitoring. Intermittent bolus. Clear? So this is the gold standard. This was called the gold standard cardiac output monitoring. How do we do this? In Swan glands you can do cardiac output. In Swan glands you can do cardiac output monitoring. How do you do that? In that you put the catheter. Okay, and just like how we are pressing cardiac output monitoring, go to pressing cardiac output monitoring. Okay, and what we do? Inject 10 ml of cold saline into the right atrium. There is a port over here. There is a port that comes in over here that injects it into the right atrium. And there is a thermistor at this end, which will actually say the blood going from here to here. It will find the decay in the temperature. So we inject it cold, it will get warmer and warmer and warmer and warmer, and the thermistor here will actually figure out how much is the difference in that temperature. You understand? So by doing that injection of 10 ml of cold saline in the right atrium, measurement of temperature 10 cm downstream, they would now plot a graph. Okay, of the temperature change that is occurring. Okay, clear on this? And the degree and rate of change in temperature is inversely proportional to the cardiac output. So by just looking at that graph, you could say if it's a broad graph, the cardiac output is low because it's taking a long time to change. If it's a narrow graph, means the cardiac output is good. Simple? That's what this particular Swan glands was all about. The Swan glands was the curve, there's a baseline, then the curve onset reaches a peak, comes down, and this is what you're getting. Right? So that's the port that you have of the Swan gland. So in your exams, there may be a situation where that Swan glands is placed, because now also liver units, now also cardiac units use the Swan glands. So in your exams, there is a possibility that the Swan glands is placed on table. You should know what the ports are all about. The ports are 4 of them. You see those 4 ports? There are even 5 ports swan cans, but usually the 4 ones are kept. Where the first port is the proximal port, which opens into the IVC, it's like a CVP. The proximal port opens into the right atrium. It opens the right atrium. That's the proximal port. Then you have a port to the thermistor. Then the third thing is that port to the thermistor, that is where the temperature machine is attached to find out temperature. Then port to the balloon from where air you inject. And third is last is the distal port which opens at the end of the swan gans. Clear? So these are the various ports. There are 5 ports also. So this is what it looks like. And this formula is used. How is this formula used? This is the gold standard. Okay, this is the gold standard. Okay, so if you look at the formula back, the TB is the temperature of the blood, Ti is the injected temperature. Blood temperature, the same Stewart-Hamilton equation. If you look at it, this TB is the temperature of the blood, Ti is the injected temperature. K1 is the constant. You get the constant directly from the monitor, and K1 and K2. And this is the change in the temperature that you're plotting. So you get the answer of the cardiac output. You got the point? So this is how the cardiac output is derived when you have this curve. Clear? Clear till now? Okay, is this proven? So what they did, this is a very, very superb experiment. They actually placed a kind of a sensor in the output of the aorta. They placed a sensor in the output of the aorta. That's how you know exactly na kitna chal raha hai uske andar. So they placed a sensor inside. That's a probe that they placed inside, and they actually compared that to the swan gans. And that's how they actually proved that it was around 1 to 2% of this one of the cardiac output. That was the only difference that they found. So it was kind of the gold standard. It got proven as a gold standard. So that was the probe that was placed of time blood flow probe that was placed, ultrasonic time blood flow probe inside the aorta, and they found out that actually it's mirroring the same thing. Okay, that's how you have to find out. That's how you have to find out. That's what they're supposed to do to actually figure out cardiac output. So they compared that to the swan gan. They compared that flow probe to the swan gans catheter. And what did they find? So they did the same thing. What did they do? They also compared, they were actually doing an ultrasound cardiac output monitoring they were trying to figure out, but at the same time they put the flow probe also. So with that, they were comparing flow probe and cardiac output validation. They were doing that. So they put the flow probe, they put the pulmonary artery catheter, and at the same time they did the ultrasound cardiac output monitoring. So the flow probe is gold standard in this case. Swan gans is what they're comparing it that to, and the ultrasound cardiac output monitoring is what they were actually doing the study about. Okay, and what did they do? They gave dobutamine. We not only want the cardiac output, we also want what happens if the patient gets cardiac output increase, if the cardiac output gets decreased, because that will actually tell you the accuracy and precision, isn't it? If I give dobutamine and my cardiac output goes from 2 to 3, I should be able to see that 2 to 3. That is what we require. If it just shows you just when there is nothing in place, it doesn't make sense. It just gives you cardiac output, nothing more than that. It should tell me the change also, isn't it? So they give dobutamine. They called it as the dobutamine challenge. And then they monitored with the flow probe and they monitored with the PAC. What ideally should have occurred? That when they give dobutamine, when the cardiac output improves in the flow probe, which is the gold standard, even in the PAC it should increase. Right? That is what they should see. What did they find? They didn't find it like that. The swan gans had a decimal precision and a very high percentage error. That's why it was all over the place. This is the flow probe and cardiac output. Ideally, if it was all good, it will all be inside this bracket, but all over the place. You understand? So it was not really giving us the right change. Okay. So it was not able to detect a 5% decrease in cardiac output. It's not good. It's not good. So at the end of the day, that was a PAC. That means when you look at PAC, it was yes or no. We could not determine whether it is right or giving wrong results. That's why the flow probe was here, but the PAC was over here. If the PAC is over here, it means to say that the sensitivity specificity is 50%. It is not good. You understand? We need to be high. Okay, so this is what occurred, and that's why there is a high percentage error when they're using swan gans. This is also because of the fact that we had the same problem at that time. Many of us, in my group itself, maybe 2 of us knew how to use it, 10 of them didn't know how to use it. So whoever did the study also, they didn't do it well. Probably that's the reason that you had so much of errors. Otherwise, if I use the swan gans, I would love to use the swan gans because I know how to use it. I can interpret the problems in it. You understand? So Jeremy Swarm and William Gans, these are the 2 people who actually I actually figured out Swan. You know how this came? Swan case. How did it come? Flotation catheter was called. How did it come in place? Flotation catheter. These two were on a beach. These two were sitting on a beach, and they found a ship going like this, and there was a sail. Okay, and they found that the air was taking the ship in the direction. There was a sailboat, and the boat was moving as per the direction of the air. So the boat was literally floating with the air. That's when they decided, let's make a flotation catheter. Okay, and they put in a balloon on the catheter, which actually in the direction of the blood it moved. That's why we were able to reach from right atrium to right ventricle to the pulmonary capillaries. Well, that's why it's called pulmonary artery flotation catheter. Occlusive catheter, flotation catheter, wedge pressure catheter, Swan-Ganz catheter. Right? And I was fortunate to work with his student, Jeremy Swan's student, with Professor Charles Sprung. He's a book written. He's written a book on Swan-Ganz, so fat book on just Swan-Ganz. Because it was his student, he only wrote the book. Okay, that way. Alright, so this is what the Swan-Ganz look like. And this technique is now called as intermittent bolus thermodilation because you're not doing it regularly. एक बार कर लिया उसके बाद वापस रिपोर्ट नहीं आएगा. एक बार कर लिया उसके बाद रिपोर्ट वापस नहीं आएगा. You understand ना? हाँ? What is right? Hello? Alright, huh? Now that was called as intermittent pulmonary thermodilation, right? It was just intermittent, not pulmonary didn't come there. Intermittent thermodilation, what is happening? From here, right atrium, right ventricle, out. Right? That's why it was called as intermittent. Now we are going to something that is new. That is called as transpulmonary thermodilation. It's different. Now what are we doing here? We are going to inject from here. It is going to go from here into the lungs. From the lungs it is going to the left atrium, left ventricle. From the left ventricle to the aorta, and from the aorta to the artery. अभी तक थर्मिस्टर किधर था? Swan में. It was coming from the top and going to the swan, isn't it? उधर का उधर ही था. It was right over here. Now what we are doing something different. We are putting it from here. We are putting the fluid from here. The thermistor is lying here in the artery. So it is going from here, from the right atrium, right ventricle, from there into the lungs. From the lungs, it is going all from the lungs, from there into the left atrium, left ventricle, aorta, out into this artery. So from here to here, the temperature differential. The thing is the same only. How much is the the temperature changing? It is the same thing, but the entire thing is going a long way, isn't it? And that's called transpulmonary thermodilation. So just to again tell you this, PAC was from here to there, whereas transpulmonary thermodilation was all from here to here to here. Clear? You understood the principle behind it? Okay. The only difference in the curve would be what? The curve will be little bit more that side. No? Time लगने वाला है वो temperature detect करने के लिए. समझ में आ रहा है? जो हम लोग को इधर detect होता है, ठक करके detect होता है ना. When it goes immediately detects it over here. Whereas what is going to happen in PiCCO or EV1000? No, the curve will start late. No. So the curve is going to start late. Your detection ही लेट होगा ना उसका. उसका temperature change detection ही लेट होगा. जो पानी हम लोग 10 ml यहाँ से डाल रहे हैं, वो 10 ml यहाँ से जाएगा, यहाँ पर पहुँचते पहुँचते उसको टाइम लगेगा, right? And then from there the temperature change will occur, and that temperature change. So the curve just moves from this side to the front. You got the point? It's so simple. It's actually very simple technology. Okay, and importantly, what we don't have Swan-Ganz related problems. Because इसमें Swan-Ganz में क्या होता था हम लोग को you would put a catheter inside. The catheter used to coil, used to cause another problem. Very invasive. It was towards the lungs. There can be problems. Hemoptysis can develop. You can inflate the balloon and cause problems. So a lot of other problems that we were avoiding by using something very simple, much more easier to do. You understand, now? Because you don't now require hi-fi equipment. You just require a simple central line, and you require just a thermistor. That's like an arterial line that you put any which ways. Right, and then follow the same Stewart-Hamilton equation. Now let's look at the equation to understand. It's slightly modified. So this TB is what? Is the blood temperature. It's the blood temperature that the thermistor is finding out from here. Right, a blood temperature which is there. TI is the injected temperature. That's why that saline has to be cold. You cannot have a difference. It has to be a proper saline, cold saline that you're going to use. Okay. K is a computation constant which is inbuilt into the monitor. It's a computation constant, and this is actually the curve. This integer is the curve that comes in. Clear? And with that they are getting the cardiac output. Clear? So when they compared transpulmonary thermodilation to pulmonary thermodilation, It was definitely precise. There was no problem. Precision of transfer thermodynamic measurements were much better than PAC. In fact, it was much better than PAC. The precision means the change that occurs. It was able to figure out much better than the pulmonary artery catheter. Not only that, one of the problems with the Swan-Ganz, like I told you, was I am doing the Swan-Ganz, somebody else is doing the Swan-Ganz, some third person is doing the Swan-Ganz. The reproducibility was not easy, was not the same. Whereas with here, the reproducibility was excellent. That means you do it, I do it, it's the same. It's the same, right? And what do you get apart from these things? In Swan-Ganz, you are not getting these values. Now you are getting a huge number of other values. Global diastolic volume, pulmonary vascular permeability index, extravascular lung water index, cardiac function index, global diastolic volume index, global ejection fractions. You're getting a lot of things here. Okay, now how does it get all these things? So let me explain to you this now. Okay, so what you're seeing over here is intrathoracic volume. Intrathoracic thermal volume is called ITTV. That is a whole volume inside. Lung and heart दोनों मिला के what you're getting is ITTV. Lung और heart मिला के दोनों क्या दिख रहा है? ITTV. Right? I'm making it as simple as possible. I can make it very confusing, but I'm making it very simple. Okay. And how does it find out that? By looking at that cardiac output level and the mean transit time of the dye, mean transit time of the water. With that, it actually figure out ITTV. Why you should know this, no? Because sometimes if you get values that are wrong, you can figure out where it is going wrong. If you know the formula. If you know the formula, you can actually figure out, अरे इसमें ये problem है, इसलिए वो value ऐसा है. You understand? If you don't know the formula, you will not know कि भाई किधर गलती किधर हो रहा है. You understand? So that's the intrathoracic thermal volume. Then the other one is global end diastolic volume. That is the volume in the heart. The volume only in the heart. That is only this part. And this it finds by slope function. Okay, it finds by slope function. Of course, each of these technologies slightly change with respect to how it interprets this. That's the difference between EV1000 and PiCCO. How it interprets this curve is slightly different. Okay, slightly different. The way it interprets the curve, the formulas are slightly different. That's why it's a different technology. Okay, the algorithms are different. Okay, but they're comparable with respect to their findings. Okay, so global end diastolic volume. All right. Intrathoracic thermal volume, global end diastolic volume. We understood this much, right? What is global end diastolic volume? So this is the difference in the way it actually figures out the algorithm. So here what it does now, it finds slopes. It finds slopes S1 and S2, and with the slopes, it's actually giving you all these things. Whereas here what it does, it is actually doing something very different. It's doing something called as DST, downsloping time. And with downsloping time, it's actually giving you the global end diastolic volume. So it's a small difference of just the algorithm. So don't confuse yourself. The volume view and the PiCCO are both transpulmonary thermodilution methods. The only difference between the PiCCO and the EV1000 algorithm is the algorithm change. Is the change in how it interprets the cardiac output and the global end diastolic volume. Clear? Clear? Otherwise, it's the same thing only. And it actually figures out extravascular lung water or the water that is not in the heart but outside the heart in the lung by looking at pulmonary thermal volume minus pulmonary blood volume. Now, pulmonary blood volume is getting from DST. So, if your injected is not right, pulmonary blood volume barabar nahi aayega. It multiplies the GEDV by 0.25 and gets pulmonary blood volume, and then minus the PTV minus PBV will give you extravascular lung water. That means pulmonary blood volume was the volume in the lung, the thermal is the total volume in the lung, total volume which includes the hilum and all these places, vasculature over here. When you take out the vasculature from here, you will get the volume only in the lung, and that is what the extravascular lung water is. Clear? Understood this? How it does it? Or no? Let's go back once more then. Okay? First thing that it calculates is intrathoracic thermal volume. That means the volume in the lung, in the heart, in the hilum, in the great vessels. So the whole volume, ITTV, it calculates by looking at all of these things. Global end diastolic volume is actually the preload of your heart, is only the volume that is lying in your heart. So it finds out the global end diastolic volume again by looking at slope function. So these two things are calculated. They have actually measured the ITTV, they've actually measured the GEDV, they've We actually measured this. This monitor has measured it. Okay, we just do it in a different way. Okay, and then after doing that, then it actually finds a pulmonary thermal volume. That means only the volume of the pulmonary system, that is the lungs and the hilum, and then it minuses out this hilum and gives you the volume in the lung. And we are concerned with that volume called as extravascular lung volume. We're not really worried about the rest. We're not really worried about the rest. We're worried about this extravascular lung volume. Okay. Now that's why this extravascular lung volume becomes very important. Now, how do I actually figure out extravascular lung volume? Okay. So it's an extremely good correlation. Gravimetric method. What is gravimetric method? Today there is a patient who dies, and I want to figure out he died because of pulmonary edema. How much fluid was there in the lung? The method is you take the lung, squeeze it out, take the water out, or weigh the lung, find out the water. That's gravimetric. Gravitational force. कितना आ रहा है, कितना पानी आ रहा है. That will tell you how much water is there in the lung, right? So they compared this method with the gravimetric method. That means they did extravascular lung water and then they weighed the lungs to figure out कितना actually आ रहा है. They found it to be excellent. The correlation was pretty good. More the gravimetric, more the extravascular lung water, more the chances of dying, which approximately normal values are 7 to 10 ml per kilogram, right? So the extravascular lung water intake we see on that monitor, 7 to 10 ml per kilogram is pretty okay. Anything more than that, the chance of dying become higher. Clear? Prognosis wise. And it correlates to multi-organ dysfunction syndrome. So that's how we actually changed the antibiotics also on that patient. We found the extravascular lung water to become higher. What did we do? We actually started minocycline on the background of SVR. We didn't take one value, we took many values together and we said let's change the. So this is how the entire PiCCO works. You understood this? That's completely about thermodilution. Any questions on thermodilution? So now the actual, how to do it, what to do, we will call them to do it. Okay? Further from here. Before she starts, we have now cardiac output we got. Now the value of that keeps on changing, no but. No, तुमने cardiac output तो पता कर लिया, तुमको cardiac output thermodynamician किया, you found cardiac output 4. But then when you're standing and looking at that patient, you're getting cardiac output change of 4, 4.5, 5, 6. How does it do that? It actually does that by now calibrating the system with the pulse contour analysis. You understand? I'll explain to you what this is. So अभी हम लोग के पास क्या आया? Thermodynamician आ गया. उसमें हमको पता चल गया cardiac output कितना है, global endoscopic volume कितना है, extravascular lung water कितना है. That is a one time you're getting that. You cannot get extravascular lung water continuously. You're getting this one time, right? But now I want my cardiac output to be continuous. So what now I'm going to do? I calibrated the system, told the system this is the cardiac output, and now the system will use pulse contour analysis to give you continuous cardiac output monitoring. How does it do that? We'll understand this pulse contour analysis because that is also part of PiCCO. Okay. So what is pulse contour analysis? So what it does, the concept is actually it looks at systemic vascular resistance. It looks at blood pressure, it looks at stroke volume which we just now measured, and it looks at the compliance of the aorta, the compliance of the artery or the aorta. Okay, and this compliance it actually figures out from weight, height, age. If you don't put these values, you will not get the cardiac output properly. Got the point? By looking at entire database of patients whose weight and height is known, they find out a compliance of the aorta, and that is fed into the algorithm here. Okay, it's fed into the algorithm. Then it looks at SVR, BP, and stroke volume, and gives you the pulse contour. How does it do that? This is your arterial line. This is your arterial line. This is your normal arterial line that's coming in. Till here is your diacritic notch. This is systolic artery. This is diastole. This is systole. It looks at this systole of this. And there are three methods to do that. The three methods. What are the methods? Indicator dilution, physical demographics. Flow track uses only physical demographics. The PiCCO, the second part of the PiCCO uses only physical demographics and calibrates it. Okay. And the last is no calibration of most case system. This system also I've used, but not a great system. So how does this work? All right. One second. Let me just go to this. Right heart, left heart. Okay. Let me go to this. I don't have it. So here it is. Okay. So how do we use this? So it works like this. So the way the normal flow track works is something like this. The arterial trace है. The arterial trace is at 2000 data points. It actually takes the arterial trace at 2000 data points. ठीक है. So एक ही trace में 2000 data points निकालते हो लोग, data points, okay, and it multiplies it by a factor, and that factor is actually a part of compliance, arterial pressure and waveform characteristics. मैंने the waveform टेढ़ा हो गया, waveform सीधा हो गया, waveform ऊपर हो गया, waveform ये बाजू हो गया, बड़ा हो गया, उसके basis पे the waveform characteristic. That means if the waveform characteristic goes bad, your PiCCO will give wrong values. You must understand that, okay? Because अगर तुम्हारा waveform बराबर नहीं है तो तुम्हारा cardiac output बराबर आएगा नहीं. वो क्या कर रहा है? तुमने पहला you have calibrated your system and you have told him this is the cardiac output for this waveform. This is your cardiac system for this waveform. Now waveform may become slightly bigger or slightly broader, but if it gets damped, everything goes for a toss. You understand? Okay, that waveform change becoming, because if you give NORAD, it will become more steeper. So that's called skewness and kurtosis. That's called skewness and kurtosis. That waveform it takes and looks at that. It looks at mean arterial pressure, and then it looks at compliance from where? From weight and height. Okay, with all this age, gender, height and weight, it gets the compliance, which it has to add into the system. Okay, and skewness and kurtosis is the waveform characteristic it looks at, and with that they find out cardiac output. There are so many studies of that, so many studies of this flow track. It is still being studied again and again, this kind of contour analysis, that the 4th generation has now come out of the flow track. Now the 5th generation has come out, I think 3 months ago. So let's now understand PiCCO, okay?
This is the PiCCO catheter. This part loop kind of thing goes inside the femoral artery, and this is where you connect the art line, and this end goes to the monitor cable. Okay, if you want, you can just have a look at this.
Show it. Show it to them. So I'll just show it to you. This is you can see it. See, this is the catheter, okay, and this got a radial also. This is femoral. The radial will be going all the way, okay,
40 centimeter.
40 centimeter long.
Absolutely.
So radial will be the longer, but of course it's long, so we don't want to put it in vascular injury and all this. But you can put radial also with the PiCCO. This is the difference in the EV1000. You can't use radial, okay. And this is the catheter that's femoral. It's got from where you monitor the arterial line, and this is the thermistor. This is the temperature. So the thermistor equipped there. This is the temperature. Okay?
So connection, I'm just sharing the notes with you afterwards.
You want to put it up?
This is the temperature housing indicate. So what happens here is we need 2 lines, as doctor said, CVC and arterial line. So we inject the cold saline through the CVC here. This is our injected sensor.
We can first understand the connections before you go ahead. Connections, yeah. Before you actually, catheter is now sitting here, right? This catheter is sitting like this inside. Okay, this is catheter sitting like this. Clear?
Yeah.
Now this catheter has got 2 ports. There are 2 ports here, right? Now this is going to this cable here. Okay, this cable here, this cable is what we require. Without this cable, you can't use it. Without this cable, you can't use it, and without a monitor that actually says PiCCO. Here, this one, orange one, it will not work. It needs to have this written PiCCO. You can see this written PiCCO. So you cannot have any module. This module is expensive actually. Okay, you have to have not only the module, you also need to have a license, isn't it? Service license. So a software. You need a software and you need a module. So you can buy a monitor, but not buy the module. If you want PiCCO, you need PiCCO module, you need PiCCO license, and you need the monitor. It's like that, the module. Clear? So now in this will go this one.
So this is the cable basically which connects with the monitor. Here, this end. This end connects here.
And if you look at the middle part, it is actually helping us to sense both the temperatures.
So first, this will go to the injector housing. One cable will sense the temperature, and second one will go here.
So when we talked about it, we talked about injected temperature, we talked about blood temperature, then we talked about slope, right? So how is it doing this? It is doing it by looking at this temperature, that is the injected temperature from here. Injected temperature from here. The blood temperature it is getting from here. You understand? It is getting the blood temperature from there. And the usual arterial line is what this is. The usual arterial line. So this is connected to the usual arterial line. This is called usual arterial line. So usual arterial line is going from here. The temperature housing this temperature is actually going to the temperature housing of this. From here it is taking temperature from the blood here. Okay, and it is taking the temperature of the injectate from there. Now you understand the entire principle how it's working? You understand? Huh?
Yes, this is the femoral catheter, which is 5 French and 20 centimeter. We have different like catheters available according to the site of injection.
So the different, there are different sites where the catheters can be used at the brachial side or the radial or the femoral catheter can be used. But depending upon the site where we are actually putting this catheter, the size and length of the catheter will be different.
So the brachial catheter is smaller, is it?
So it is 4 French and 16 centimeter. And the femoral is 5 French and 20 centimeter.
And the radial will be all through, right? Go till there, no?
Yeah,
Radial go
all
up till
over,
there.
yes.
It will, from here it will start and it will
Go till that end, yeah.
Yeah, which is the longest, 4 French and 50 centimeters. So one more thing is, we are the only providers for pediatric, which
Pediatric,
is
yeah, pediatric.
only femoral one, and that is 3 French 7 centimeters.
The distance will be different if we use different sizes.
Every catheters are different.
No, for that calculation.
Calculation.
Yeah.
So it is the same thing only. The difference is this is going in the artery. We are injecting in the vein. No, we are injecting the vein. It is going from right heart, lungs, coming out.
Yeah.
We are one monitoring in the femoral artery, the other we are monitoring in the radial artery. There is no difference. You got the point, right? It is just monitoring at an area where it can be kept free, where it can be sensed. वो इधर रखा है ना तो वॉल को लगेगा. You understand? तो उसको बड़ा आर्टरी लगता है जहाँ पर वो आराम से बैठ सकता है. You understand? ये तो इधर आजू बाजू लगेगा और फिर bolus drift, thermodynamic drift, bolus drift आते रहेगा. You know drift, whatever that drift is called, because drift आते रहेगा. So that's why you need that to be in an artery which is big. इसलिए वो यहाँ से इधर तक पहुँच रहा है. समझ में आ रहा है?
Graph will be closer to the base.
Not much of a change. After all, aorta यहाँ से निकल रहा है ना. Aorta यहाँ से निकल रहा है, femoral को जा रहा है. इधर भी जा रहा है तो थोड़ा सा closer नहीं होता. That's not going to change anything. It is not going to change because we have now it has found out that by radiation it's not going to change the graph as much to change the cardiac output. You understand? The appearance of the graph will not change. For example, cardiac output अगर खराब है तो वो broad ही रहेगा. Cardiac output अच्छा है तो narrow ही रहेगा. हाँ, only the indicator कहाँ पर पहुँचता है वो शायद थोड़ा सा change हो जाएगा. That's all.
Volume of normal saline required
Will be the same. No, it will be the same only. At the end of the day, what we want a finite volume that is going, and we just want to find the temperature decay. We just want the temperature decay. कि temperature कहाँ से कहाँ change हो रहा है. तो volume remains the same. Volume does not change.
What are we looking for is the temperature difference should be more than 0.2 degrees Celsius. That is what are we getting.
So now you must also understand कि जब तुम inject कर रहे हो, so don't inject it fast. Don't inject it very slow. Because you inject it fast, it will go fast inside. You inject it slow, it will go slow inside. It might change the characteristics. So on an average, you should finish the injection in 7 to 8 seconds. You know, something like that. Okay? Yeah.
We have this, but you have already covered this.
We have seen the connections. Now we are looking for this monitoring part. So first, very important step is to put the patient's demographics. So how we'll do is, I have kept the monitoring demo mode. We'll go in.
This is the crucial part which you wanted to understand.
How do I show them everyone?
No problem, at least you got to keep it.
Okay, so for patient demographics, we'll go and admit patient. Just put the name and age, gender, etc. So I'll put it as test. Okay, then date of birth. If you don't know the date of birth, just put the year. Let's say 1960 something. Right. And then we'll put the height, which is around 175. Enter. And then weight. 70 kg. Okay, and then confirm. Now, second most important. So first is patient demographic. Second most important thing is to zero the arterial line and CVP line. How we will do it? Just put on the arterial line, press on it, and just make the tap connector open to air, and then do the normal zeroing as you
They know
do.
the normal zero.
Yeah. So zero the ABP line and the CVP line. Third thing is just you need to add the PPV value on the main screen. How will you do that? Just remove one of these value.
See, the important parameters which you wanted to see continuously, you have to get those onto the main screen. Then only it will give you a continuous value. If something at the end of the thermodylation curve,
Okay,
you will
just
find a
I'll
chart.
just change
So
it
that will give you a
to
still values. That
change
will not
numeric, and then I'll see for PPV. So first thing you need to activate the PPV, and that's where go in main setup, measurements, and just find for PPV here. So just it was disabled, that's why we were not able to get it. So enable it, confirm, and now just change any numeric, like any blank space you can change it to. Pause it.
pause कर दो.
Pause.
Just a guess.
All are showing.
Only that.
Okay, but which one is having severe pulmonary edema?
Middle one is later.
Exposure is not that good.
Okay.
Must be middle one.
So you can guess between last one and first one.
Third.
Third one is having.
Third one.
Okay. So if we'll have this extravascular lung water index with us, we will understand what is the value of that, and we can just see which is the patient which is having the severe pulmonary edema. So this indicator will definitely help us to understand this condition. And as Sir said, we have this normal value till 7 ml. So you can see the first patient is in severe pulmonary edema. So just wanted to grab attention for this. And also this ready-made charts are available. If I get your email IDs, I can mail you this. So you can keep the soft copy with you. Yeah, you can also tag, but for your information, I'll mail you. You can also download and keep that with you.
Which is our third step. So we have got this, and then just select the CCO from the what I wanted to show you is the CCO from the atrial line should be as same as your main screen, right? So just look for then just go and when setup CCO, the setup CO. When you will connect the
You finished these values now.
yeah.
So this now you make a chart of this. You make a card of this. One card, okay? And that card now you put it on the machine. You want
Your arterial line and CV.
Yeah, how did the patient demographics go once more? The date, birth, okay.
And your height and weight.
Just for my knowledge, when I do this, I've taken the mobile caregiver on this. It comes on my mobile,
The parameter will come onto that.
but this will not come.
No.
Only the
Name
parameter.
will come.
If it is already configured, then it
If the name is come here, that will come, no?
absolutely.
That will
Yeah.
come.
Yes, yes.
Okay, so now you understand why you have to fill this. Because if you don't fill it, your cardiac output will be all garbage.
Yeah. He has already informed, explained the importance of demographics.
Okay. So Alia, what were you sleeping or when she was showing you? Come sit.
Just I'll put the
These are come out.
first
Enter.
name is Ed. What Gender is important.
Why is it important, Hemant?
बॉडी वाटर कंपोजिशन अलग है
Nay, why is it important?
Formula is different.
No, why it is important to put that? Because with that it actually gives you the compliance. Iota ka compliance, artery ka compliance, it takes from demographics, from age, gender, all of these things. Okay, so you can't not put it properly. You understand? समझ properly क्यों कर रहे हैं आप लोग? हाँ, ठीक है?
ठीक है. And then height and weight. Height say 170 something. Weight say 70. So these 4 demographics are very very important. Just put on confirm. Second thing, as I told you, just zeroing the AVP and CVP, your arterial line and CVP line.
So for my knowledge, if I put ART, it will not work.
It will work. Just you need to change the. I'll show you afterwards.
Okay.
We'll see
So
you.
just what I'm asking is here is written ABP. Okay. This is ABP. Okay. Remember this. Okay. She will come to that later. Okay.
Yeah.
Just explain it right now. The
So-
label has to be same. Whether you use it ART or ABP.
So if
The
I
label has to be same.
Yeah.
The monitor should know about that from which instance he has to pick a signal. That's it.
The cardiac output basically.
The path, yeah.
The path from where to you understand now because the cardiac output is coming from this trace. Okay, so if you put the cardiac output to take from ART,
Right.
it will not give you because the cardiac output is coming from ABP.
Yeah.
You understand, na?
Correct.
sometimes it happens like you are using 2 arterial lines. One name is AO, let's suppose, and other one is ABP. So you should give the path to the CCO output. Like where should it come from? So for that, if you need to change it, just I'll show you once. This is the option. Just click on CCO on the main screen, and this is the option CCO from. CCO from. You can change it from
You can
AVP,
change it.
AO, ARD, any. Like you just have to decide the path.
Okay.
Okay. Then third thing, PPV should be enabled on the main screen. You need the PPV value here on the main screen.
This PPV will be from the arterial line or the ABP?
This will calculate from this your cardiac output itself. Like see.
No, the PPV will be from your arterial line.
Arterial line,
Your
right.
your
And I think
PPV
you need-
will come from your arterial line, only,
line.
nothing more. Okay, this is the same PPV that we use otherwise, nothing different. Okay.
There are 2 options. And your patient should be intubated on the ventilator. Then only the PPV value. will come.
No. So PPV will come anytime. We use it for certain things. Let's go ahead. Yeah.
Okay. Now just go on the setup CO. Then setup CO. If the your cable is connected to the this catheter, it will directly sense the method as transpulmonary. Second option is right heart. You just need to.
So understand that transpulmonary is what? Is what we're doing. Right heart is what? Swan gas.
Swan gas.
Okay, so if you put a swan
There are
gas,
two
you will get that. Okay.
Yeah, and the measuring mode should be standard or auto, that you need to decide. Auto will like automatically tell you where to like what will be your next step. Like it will say prepare the next injection or prepare for the next dose, etc.
Just to add, see. Okay, the normal thing is a transpulmonary. You will have to select it before attaching to the catheter to the monitor line. Because once you connect that option will get locked.
Yeah.
And you can't change it.
It will automatically detect actually the when
But if it is there, you have to select it on
Yeah.
a prior basis, then automatically it will get
So if
locked.
we, for our practical reasons, when we are attaching it, we directly transfer it to
That's
the
what
catheter.
you
Yeah.
don't need to worry about that part.
Also, you need to look for the alarms what you are getting, like alarm limits. You can change it, and then third thing is you just go in cardiac output option. Now here is where you will do the thermodilation method. So I'll just quickly explain what this is showing. This is your trials, like for 6 trials you can get. This is the average of 6 or whatever you
So
are.
whichever trial that you do in thermodilation, you will get one graph here, one graph here, one graph here. So normally you need 3 trials, okay? For any device that we
Minimum
use,
3.
for echo, for ultrasound, whatever we are using, we use how many? We use 3, right? So 3 is what we require. We don't require to do 6. I'm seeing you're doing 6 down there. 3 ही करने की जरूरत है,
Yeah,
ठीक है?
maximum you can go to
And
6.
what you're seeing here is the average. It's important that you look at all these three. Why do you require to look at all these three? Because we don't want the values to be much different from each other. If your value 1 is 2.1, other is 5.2, means there is something wrong in the way you are injecting. So the graph should look the same, no? Because it's the same cardiac output. Agar you are injecting 3 times, the graph should look near about the same, isn't it? If it looks near about the same, the value should be near about the same. So within 10 to 12% of the original it has to be. So if your cardiac output is 3, it has to be 2.8, 3 or 3.2. It can't be 3 and 4. You understand? Then your average will become wrong. You understand? You'll not know which value to take. Okay? That's why you have 3, you can select and deselect. You understand?
Yeah. So this is the injected volume. Like you can change it from, see, this recommended injected volume is 15 ml. Why it is like recommending like that? The alarm came because we have put the height and weight of the patient. According to that, the body surface area, what monitor is suggesting to get the volume for 15 ml. Like to inject the volume, cold saline volume, it is to be 15 ml.
So it comes directly over here, is it?
If
You
we
can
press
change it
it
as
now,
well.
if we press it, it will show
It
you
will show
the
you what is the device.
environment. Yeah. So we'll just.
So we need to press it up. That means we need to press it and see.
Yeah, you need to press it every time. Like for obese person or patient, the value can be 20 ml also. If the patient body weight and the height is more. Okay, then it will suggest accordingly. This is body surface area, which is it has already calculated. Now here you can see the indications. Like it now it is saying ready for new measurement. So just start CO. Now it is saying the stable baseline, inject now. So I'm just doing the demo inject. What you want have to do is inject it from CVC line as I'm
from there.
from here. This one. This is your CVC line.
So now you see it creates a trace. You injected here, but it detected here. You injected right here.
Yeah, right here. The marking comes.
And now getting a trace. That's the trace that you get, thermodynamics. Okay?
This is the graph. Okay, so it is showing now weight before starting the new measurement.
So now you see now all these
So
values.
this is just demo thing.
So now you see these values. Now you can understand what is extravascular lung water index. What I explained to you on.
So
okay?
these values are for this trial only. Now what it is indicating is ready for new measurement, and then we can start for a new trial.
Wait. But when we are doing any kind of thermodialysis, just have a look onto the temperature difference which we have mentioned. It has to be 0.2 more than 0.1. It will give you indicate immediately. So if
Yeah.
it is coming below that, so that means your trial is wrong. You have to
And
perform
you
the
can
next
delete the trial from the average marking. I'll show you how to do it. We'll take the second trial. We'll just click on start CO. Same. Now it is saying to inject now. I'll just demo inject it. And you can see this marking, the cursor which is moving. As soon as the injection gets detected, it will show. And the graph will start later. So your injection should last till 6 seconds. Whether it is 15 ml saline, 20 ml, 10 ml, it should last till 6 seconds. 6 seconds के अंदर it should get complete. So these are two different values. First one is 17 and second one is 8. Like, there is lot of difference.
इसमें टेम्परेचर का एक बार we can check क्या ऊपर
Like
वाला जो
what you
temperature
Post injection
temperature हाँ
this is 0.25.
अच्छा उधर
हाँ, the difference it will show you here.
अच्छा
Now to reject or accept the trial, just click on this graph. It will get if it is red, it will get deleted from the average. To accept it
But
again,
on
just
screen
click
it will
on
be
it.
shown.
It will show on screen, but here the average values are there now. It will not calculate in your average, basically.
So that will not get considered into the averaging part. That's it. The only green will get.
So this green means it's proper, na? This green tick.
is selected.
Green means it is
No,
selected.
no, this
in-
green
in
tick
this-
mark here.
Green
Yeah,
tick- yes.
here the
The tick
green
mark.
tick marks means it is selected.
It is the right thing.
Yeah.
So there is a green tick mark here. Can you see a green tick mark here? That green tick mark means
This
that
one.
value is at least the process has been fine.
Fine.
Okay.
Or whenever here it will show as NA or any other thing, a cross mark will be there. So you need to look for your ABP label or patient demographics or any other thing like PSA and any other thing, any other complications must be there.
So, just one more point. Whenever you're doing the thermodilation, you're injecting a cold saline, try to select the middle lumen so that to avoid the turbulence and something like that.
Okay, so for now I'm getting these two trials, and then after you will be satisfied with your trials now. Then you just have to click on Save CO and calibrate. The go in hemocal option, and you will get all these values. It will show the hemocalculator values. Hemocalculation.
Accept, confirm, second.
As I showed you, right?
So that is accepted for the particular modulation. Very you can select it.
So in demo mode, PPV value doesn't get calculated. So here the few values are missing because it is in demo mode. But on patient it will not happen, as we have already seen.
You
PPV
can change the
values.
CDM and PPV value as well because we have that option.
You cannot change it from here.
And when we are trying to do any kind of thermodilation, please don't do it on MX 430. Okay.
This is 450.
This is 450.
This is new monitor in the new.
And in which ways we are going to put that label onto it. So,
Yeah. And you need to see the software options.
So now you understood all of these values, right? These things. Now, so see, if you see, because you put the height, weight, you've got the cardiac output. Now this cardiac output she has got from thermodilation. This cardiac output she's got from thermodilation, right? Now उसके बाद जो cardiac output change हो रहा है, अभी इसके बाद इसने cardiac output 13.1 मिला है, but you're now showing 6.4. It's you're going to keep on changing. Cardiac 11.5.
11.
It is changing. Now why is this going to change? Keep changing. It's going to keep changing based on your arterial line.
that is
Pulse count.
Pulse contour, which we discussed. Pulse contour. समझ में आ रहा है? तो हम लोग का ये जो value था, this is ideal, but this is the right value. But now I want continuous. Since I want continuous, बार बार computation तो नहीं कर रहे हम लोग. तो अभी क्या कर रहा है? It is using that value, calibrating it to that particular arterial line, and then using arterial pressure contour analysis, arterial pulse contour analysis. We are looking at compliance, body surface area, height, weight, gender, and all these things, which is now giving you this cardiac output, which keeps on varying. You understand? At this stage, now one of the problems is many of these, some of these values must be careful of. Like for example, the systemic vascular resistance. The SVR is not a function of directly that is derived from here. It is derived from CVP. Okay, so if your CVP is wrong, no, everything else will become wrong. SVR ka. Remember this.
That's why we do the zeroing before starting.
No, even after that, if your central line is inside your right ventricle, if your central line, which usually is inside your right ventricle, very often, very less we keep it outside. I saw you also the other day, rather than actually using the plug point, you have to use a stopper. You are not using the stopper, you're putting it directly inside. When you put it like that, your central line will be right. When you put a central line, apart from the V, there is a small stopper. So, you have to take out the central line up to say 10 or 12. Tab jaake it remains in right atrium. If you're going to put the whole line inside, it's going to be the ventricle. So when it goes to the ventricle, the systemic vascular resistance is actually taken in from that particular CVP. It's one of the part of it. So if your CVP is hitting against the wall of an artery, of the vein, or the CVP is in the ventricle, then your SVR will show all wild and very difficult signs. Similarly, even your extravascular lung water index will also be problematic. All these things, all these derived parameters can be problematic if your right heart is not working well. Why is that so? Because you must, like for example this, there is, over here you see there is cardiac index, there is cardiac index here. Can you see the cardiac index here? Now cardiac index, we know the normal values. Go back to your earlier chart. You have function also, no?
Yeah. This
See, you have CFI here, CFI, cardiac function index. Okay, this is something that is there in this monitor, PiCCO. It's not there. It was not there in an earlier monitor. So cardiac function index over here is basically your ejection fraction. It is like your ejection fraction. You're understanding? Now the problem is it is global. It is, how does it monitor this? It monitors by looking at global end-diastolic volume. I remember I told you global end-diastolic volume, the whole heart. Global end-diastolic volume, intrathoracic thermal volume, extravascular lung water, and global end-diastolic volume. So the heart is the global end-diastolic volume. The global end-diastolic volume, the global end-diastolic volume, it takes the global end-diastolic volume to find the cardiac function index or the ejection fraction. That means to say, if your right heart is not working, then that cardiac function or the cardiac ejection fraction may not be right, because ejection fraction, what you're looking at, left heart.
Left heart.
You understand? And how is it deriving CFI from global end-diastolic volume? Now global end-diastolic volume is right as well as left. Are you understanding? What we want left. हम लोग को left चाहिए. Now if you have a patient on very high PEEP, when you have a patient on very high PEEP is very high, there is right ventricular dysfunction because of high PEEP. Okay, or the patient's pulmonary embolism or something like that is there. Like for example, the patient that's down there, you will have right ventricular dysfunction is going to be there because he's on very high PEEPs. Okay, some dysfunction will be there. So that's why an echo becomes very important. If you can figure out right ventricular dysfunction, you say, okay, then your cardiac function index is fine. But if there is right ventricular dysfunction, then your CFI will become wrong. Cardiac function, where was gone? So no. CFI becomes 4.6. That will become wrong. You understand? Now this 4 points, anything less than 3.7 means low EF. Anything less than 3.7, okay, it means low EF. You understand, no? Anything less than 3.7 is low EF. So here be 4.6 means normal. Okay. Another value that you get here, and also we used to get in the other monitor, was the PVPI. Here, see, PVPI, pulmonary vascular permeability index. This actually differentiates hydrostatic pulmonary edema from hydrostatic pulmonary edema from permeability pulmonary edema. You understand? If it's low, it's hydrostatic. If it's high, more than 2, it goes in favor of leaky capillaries. This is hydrostatic. So if you have extravascular lung water that is high, that is more than 7, 8, 9, or more than 10 maybe, okay, if that is high, okay, there are 2 reasons for it we discussed. There are 4 reasons for that matter, but for our patient we need 2 important reasons. Is it hydrostatic or is it leaky capillaries? In intensive care we are worried about whether it is leaky capillaries or whether it is hydrostatic. Now with the pulmonary vascular permeability index, we have a kind of an estimate ki if it's low, it is more of hydrostatic. That means I am having left heart pressures that are problematic. And if it is high, it means it is leaky capillaries. I need to do something for that. Are you understanding? So with this PVP, I get that important value there. You understand? Now I can't have these values as blown up, no? Anytime. I can't have only these 3, 4, whatever. I can't have like big numerics come on this. That we can't get. So if I want the cardiac output it is going to be small only. It can't be big. Like otherwise, we have 4 values. You can make big and keep.
Big and no, the big value number is not.
Big is not calculations. And you can see the whole thing.
How did you get the SVR and all calculation? That didn't come the first time.
It will come provided the central line. See what happens many times. No, what happens many times is you have injected and then you have closed the port and kept it. So if you have closed the port and kept the injected now, the CVP is not getting traced only. Since there is no CVP, there is no SVR. Because it is a function of the SVR. You understand? That's why you need to actually, after you finish that injectate, you keep it open, let the CVP be monitored. If the CVP is not going to be monitored, there will be no SVR.
Just go and perform care and you'll get the values if they are not getting.
So if you go to this and omit the CVP, make the CVP 0 here in the demo mode. You cannot do that. Right? Can you do that? Make it 0. Make it 0. In fact, if we take it off, let's see what happens.
0 and perform care.
So 0, make it 200 maybe, make it 300. So CVP, let's make it 300. Like it's blocked, the catheter is blocked. 300, okay? So, and let's see your calculation. Perform calculation. Is the SVR coming?
SVRI is not coming.
It's not coming. You see that?
SVRI is not coming.
You understand it's not going to come because what's happened over here? Your CVP is blocked. If your CVP is blocked, your SVR is not coming. That's why this monitor is not, this calculated parameter after all. Okay, so it's not going to show your SVR. See that?
Yeah.
You got the point. So that's what would have occurred. Probably wouldn't have turned the stop catheter would not be quite patent, which should have caused this.
So few things are there, and we just need to
हाँ.
highlight. Your injection should be fridge cold,
हाँ.
and like maximum, like it should be able to give the difference,
हाँ.
like 0.2 difference. And the second thing is, before like doing the thermodilution method, just look for your CVP line. It should be cleared. Like any infusion pump or anything should not be interrupting between the process. Infusion pump and ventilators mostly do that. If the patient is on ventilator or infusion pump. And the second thing is, this cannot work on IBP.
Yeah.
Well.
So it will not work in IBP.
And
Similarly,
insulin as well.
and in CRRT also, it will work, but will not be accurate. So if say you have an IBP on, you can still use it. We've used it. How do you use it? In IBP, switch off the IBP, do the thermodilation, see the cardiac output, but don't see the continuous cardiac output. You understand? Huh? Because why it will not work with IBP on? No, why it will not work with IBP on? How does it monitor the continuous cardiac output?
Pulse.
Looking at the pulse. What happens to your IBP pulse waveform? It completely changes, no? It becomes different, no? So if your waveform becomes different, will it be able to identify your continuous cardiac output? No, because it looks at waveform characteristics to actually monitor your cardiac output. Are you understanding? So it cannot do that. Okay, so it cannot work with IBP. So in that case, what do? I switch off my IBP for that particular moment, put it on standby, do my thermodilution, see my values, and go back to my IBP. So at that time, only my values of that are significant. It still makes a lot of sense. CRRT values are not very accurate. It's not very accurate, but I may as well look at the trend of it, no? See, if I am not accurate, I may look at the trend. I will, because the precision of the monitor is very good. Since the precision of the monitor is very good, what I am seeing now, I will see later on. So if my values were wrong, it will be more wrong or less wrong, right? So I can see the trend. I can see what is happening there. So it's not this way that I can't do it on CRRT. The accurate values may not be accurate, but everything else you will get. Why the values will not be accurate, Hemant? On CRRT? Why the values will not be okay? Kanchan? What is the method?
Blood flow.
What is the method? What is the
filtration.
No, what is the method TPDD? What is happening?
Transfer.
तो क्या हो रहा है? ब्लड कहाँ से जा रहा है? इंजेक्टेड कहाँ से जा रहा है?
Blood is going out.
Continuously, so it will affect the temperature.
Yeah, because वो CRRT ब्लड खींच रहा है बाहर, तो ये कहाँ जाएगा ये ब्लड? ये ब्लड कहाँ से जाएगा, किधर से घूम के जाएगा? तो वो जो हम लोग को जो टेम्परेचर डीके चाहिए वो बराबर मिलेगा क्या? नहीं मिलेगा ना? You are understanding? वो टेम्परेचर No, we can't. The blood volume is half outside. Your blood volume is half out. 300 ml is outside. If your half your blood volume is outside, your temperature is completely different. Now. So you may not get the right values. You can't do that.
Temperature difference won't be that accurate.
Temperature difference will be accurate, but the problem is it will be completely muddled because your CRRT circuit में पानी चला जाएगा. ऐसा है वो. So you can't. That's why you can't use it with. You can use it with CRRT, but it's a problem. So what can you do if it's atrial fibrillation? So it's a good question. What happens if it's atrial fibrillation? Why are you asking me this question?
That patient has.
No, but why are you asking me this question?
Because it's pulse control analysis.
Exactly. So because it's a pulse contour cardiac output analysis, arterial pressure. Okay, arterial pressure contour. It is looking at the waveform. What she's saying is atrial fibrillation will have different waveforms because you have different tuck, then small, then big, then small. If it comes like that, then obviously your continuous cardiac output will not be right. But what will be right will be the thermodilution. So you can still follow your thermodilution because thermodilution is after all just temperature decay. You understand? So you can still follow thermodilution, but you cannot follow your continuous cardiac output monitor because you have got different waveforms. Simple. So you can still use it with atrial fibrillation. So that was what occurred with this patient down there. Patient went into slight atrial fibrillation and someone called me up saying the cardiac output is 12.2. So when they called me and said, cardiac 12.2, I said, क्या चल रहा है ECG पे? तो ECG पे atrial fibrillation. Then I said, okay, ठीक है, and I kept the phone down. Are you understanding? Because why it was showing 12.2? Because now it is actually looking at contour. Then we did a thermodilution, it was normal.
Okay, so these readings are valid till 8 hours. After 8 hours, you need to do the thermodilation again.
So when you do a thermodilation to get it again right, when you anytime do a thermodilation, the position doesn't matter. You can keep it at any position you want. Today I saw them actually giving supine position and doing it. Not required. Please don't do that. अब वो patient को actually propped up करने का था, उसको supine करके हम thermodilation कर रहे हैं. Not required. Keep him in the same position only. Don't change anything. Okay. First thing. Second thing is when you do a thermodilation, go and first zero all the lines. सबसे पहले zero करो line. The process is zero all the lines that are there. Properly zero the lines. Anyways, every 8 hours you have to zero the lines. So that protocol anyways has to be in place where you zero the lines. The third thing that you do in this case is what? You flush the lines. You flush the lines. So you flush the lines. Then you go ahead and do a thermodilation. You understand? Let the process remain the same because otherwise you will make mistakes on thermodilation and then every cardiac output after that will be wrong. Now you understand, no? Because if I do the thermodilation wrong, everything after that will turn out to be wronger and more wronger. You understand? Because it will now calibrate it according to that.
So there was the one step which we missed. Okay, you have to do again from the start to end thermodilation process. Then only you will get cardiac output. So let's say if we have not put a patient demographics, okay, but after that we have done the thermodilation curves and everything has been done. But just because of that, the patient demographics were not there.
This
You have to
happened.
Do the again
No, this happened.
whole thing.
This happened 2 days ago.
Yes.
This happened 2 days ago
That's what I
where
meant.
we did not put the demographics of the patient and since we
Like,
didn't put the demographics.
when I was asking the concerned person, he or she was saying that the demographics were put. What they have entered was last name, first name, height, and weight.
And UHID. So
What
because
we
that is what they
need is
normally do.
gender and
Age.
age. These two are also mandatory, equally mandatory things.
You understand? That's why
Every
you
time we
do.
do thermodilation.
No.
Once.
Only
once
once.
only. See, if the same patient is there, then the
There
demographics
is
are
no
already
need.
there. You have to just do process with the thermodilation.
Any questions here now? Any questions on the technology? Any questions on?
So, just one thing. Here, as he said, the tick marks are coming, the values are appropriate. When the cross marks come, or there is this thing, so as you can see, the like the letters are CAL, CAL. It might come as NA, not applicable, or EXP. What EXP means is the values are expired. Like the previous values are expired, and you need to
New
take
fresh
the
value.
fresh
So
value.
just this comes to my this that there is also the troubleshooting of this. So इसका जो troubleshooting का ना एक card मेरे को लगेगा. Okay, like sometimes they come over here ETBI high. So when ETBI is high, your problem is right heart or your problem is injectate or something like that. So उसका troubleshooting आता है. So I will require that also as the card.
Yes.
There are only 3-4 sub.
From the trends.
So maybe you change this to cardiac output. Maybe change this cardiac output. Change the group. Change the group. Change once more the group. It may be there. We may be able to. So it's important what she says. See what even the volume view does is it gives us a trend. What she's saying.
Right.
So it gives us a trend that says cardiac output ऐसा. There's a proper graph. It may be there on this also, but how to do it we need to figure out. Isn't it? Histogram भी रहेगा. Histogram भी रहेगा. So we need to figure out how it comes. It's not. We'll have to.